Tēnā koutou, kia ora koutou katoa. E nā manahiri matararahi, e nā hoa mahi, e nā tauira, e nā kai tautoko, e me nā hoa. No mai haere mai ki te whare wānanga. A very warm welcome to you all, colleagues, students, our broader public community, to the inaugural lecture of Professor Nancy Bertler, an internationally recognized professor of earth sciences from the Antarctic Research Centre here at Te Herenga Waka, Victoria University of Wellington. I'm Professor Margaret Hyland. I'm Deputy Vice Chancellor of Research, and it's my pleasure to welcome you here this evening. Inaugural lectures are always special. They're our opportunity to celebrate our new professors, to hear their passion for their research, and to learn something new. It's one of my favorite parts of my job. And tonight is extra special because it's my first time to introduce a new professor. And I couldn't be more excited than to be introducing Nancy Bertler, who's somebody that I particularly respect and admire. In a minute, I'll tell you about some of the amazing achievements that have led to her promotion to professor. But I first wanted to just pull out one in particular that resonates with me. And that's her role as director of the Antarctic Research Platform. So the Antarctic Research Platform, if you're not familiar with it, is a $49 million investment by government. It pulls together about 100 researchers from across the country, from 7 universities, from 4 Crown Research Institutes, and supports about half of our research capability in this particular area. I was in MB as chief scientist when it was being established, and I think it's fair to say there was a certain amount of nervousness about getting it right. I think previous platforms in other areas had not quite worked the way they'd expected them to. And there was a recognition that leadership was going to be a really important part of success. Leaders of this kind of large, complex, collaborative venture need to be more than just highly respected researchers. They need to have the trust of many different and sometimes warring research communities, stakeholders, and the funder. And they need to be able to pull these diverse communities together to achieve some pretty ambitious goals. In other words, there need to be somebody pretty special, somebody like Nancy. And I think the success of the platform is a great tribute to her leadership. Professor Bertler has been a part of our university whānau since the early 2000s, completing her PhD in geology here in 2004. She's a cross-institutional leader and is well known for juggling many roles around Aotearoa. We share her with GNS Science, where she is a principal scientist. At the university, as in the Antarctic Research Platform, her leadership has been effective and invaluable. She's responsible for developing our ice core program and research facilities through her collaboration with GNS, for developing our undergraduate course on climate change that educates the next generation of climate leaders with the tools to determine the future of Aotearoa's communities, environment, and economy, and for developing these leaders directly and personally, having supervised 7 masters and 12 PhD students. Professor Bertler is a trusted advisor beyond the university as well. She regularly serves as a scientific advisor for MFAT delegations to international committees, notably forming part of the delegation to the 44th Antarctic Treaty meeting last year. She regularly provides briefings and presentations to ministers both domestically and internationally, informing our leaders of the latest in Antarctic research, and she's chair of the International Science Advisory Panel of Securing Antarctic's Environmental Future. It's no surprise that Professor Bertler is so highly sought after and well regarded. As an early pioneer in targeting and interpreting ice core records from Antarctic coastal regions, her research expertise is preeminent. She's focused on understanding Antarctica's response to and its ability to influence global climate change. Very deservedly, Professor Bertler's research excellence has been recognized several times over. She received the Prime Minister's Science Prize, Wellingtonian of the Year Science and Technology Award, and the 2016 Sir Peter Blake Leaders Award. We are fortunate to have Professor Bertler as part of our faculty here at Te Herenga Waka, and fortunate also to have the opportunity to hear from her tonight. And the focus of Professor Bertler's inaugural lecture this evening is how Antarctica's ice sheets have revealed critical insights into our future and why the response is a matter of urgency for us all. Antarctica, magnificent, vast, timeless, and elusive, plays a critical role in how Earth's climate will evolve, and it's people like Professor Bertler who play their own critical role in understanding Antarctica's. It's my pleasure to welcome to the podium Professor Nancy Bertler.
Ena mana, ena reo, ena karanga maha o te wā, tēnā koutou katoa. Ki mate kua whenua tēnei, haere, haere, haere atua. Ki mana whenua o tēnei rohe, ke te mihi. Kia tātou katoa, na hunga whakahira-hira, tai tāwhiti, tai tāta, nau mai, haere mai. Ko Nancy Bertler toko ingoa, nō reira, tēnā koutou, tēnā koutou katoa. Ngā mihi, Margaret, for the very kind and somewhat flattering introduction. I sort of could feel my shoulders buckling under the very nice things that you said. Colleagues and friends, thank you so much for coming today. It's really lovely to see you all here on this Wellington evening. And I would like to start by pointing out a couple very special people. I'm really proud that my mom, Sissy, attends today's meeting. My mother is one of my superheroes and a most important role model. Also, my sister, Janine, would have liked to be here today, and she is a huge source of endless inspiration for me. And of course, my wonderful partner, Dean, who many of you will know as well, long association with Antarctica and passion for research, and sort of who has the ability to pull me out into optimism if some of the future can seem a little bit dark. Today, we are very well familiar with the concept of standing on the shoulders of giants, and I think this is normal in science. We know that we're contributing to a body of work that those that came before us have developed. And the nice mihi-mihi that the wonderful Professor Sandy Morrison from Waikato helped me to put together acknowledge those that came before us and the family that we build around us to advance the knowledge and to explore new knowledge. With having the privilege to be part of the Antarctic Research Center, really ingrains these values, and I would like to highlight in particular Professor Peter Barrett. Peter, of course, is the founder of the Antarctic Research Center some 51 years ago, and has instilled huge values that are valid in the Antarctic Research Center today. When I called Peter in the late 90s while he was in Antarctica to ask him whether it would be a good idea to add an ice core record to the Cape Roberts project that he was busy leading at the time, the logical answer should have been, that's ridiculous. But Peter somehow saw a possibility in this. And so Peter, along with Paul Majewski from the US, Tim Naish, and Alex Pine, this remarkable group of people have encouraged me, guided me, and supported me to build the ice core capability in New Zealand. Of course, as we started this journey, the fauna became bigger, and people on this slide really made instrumental contributions to allowing us to develop the science, to develop the capability to have access to Antarctica, and to get it right. And really, as this program evolved, my biggest sort of pleasure in this was really working with the many, many early career researchers, brilliant, determined, and just so smart, contributing in huge ways of the knowledge that we have as a whānau together developed and advanced. So I think like any of us, when we give talks, we know that we are presenting on behalf of a large community. And so I just wanted to share with you how humbled I am to present on behalf of this wonderful, nice, large community. Okay, to the talk. I thought I'll lead you through a journey where I demonstrate how important Antarctica is for us to understand current climate change, to provide a baseline, a barometer to which measured against how hot the world has become. And then to explore how this change is also affecting Antarctica as a climate change victim in its own right. But of course, Antarctica's response has global consequences, and it does because it is also a major climate driver. And then really conclude on how we have transitioned now to predicting climate change, to live in the age of climate change consequences. So as an ice core person, I talk a lot about ice, perhaps more than other Antarcticians. So I thought it would be useful to just very briefly summarize the three major groups of ice. Of course, there's many more than those three. But there's an ice sheet, so this is snow that falls onto a continent and then accumulates up to thickness of 4 kilometers that slowly makes its way in a slow journey to the edge of the Antarctic ice sheet. When it hits the ocean, it starts to float, and this is the part that we call an ice shelf. They can still be over a kilometer thick, but they comfortably bob with the tides. And then sea ice is frozen ocean water that just freezes when it gets cold enough to do so. We have the big Antarctic ice sheet and the smaller brother, the West Antarctic ice sheet. I'd like to take you on the journey with the project that I have become very entitled, or not entitled, that's really the wrong word, very close to, and have been privileged to be the chief scientist for the last decade, the Roosevelt Island Climate Evolution Project. It's a huge collaboration, many nations are involved, many institutions, and it's hugely interdisciplinary. We drilled an ice core from this beautiful little flat pancake, Roosevelt Island, at the northern edge of the Ross Ice Shelf, about 1,000 kilometers from Scott Base. And the focus of this project was really to understand, like many other researchers at the time and still do, how close the West Antarctic ice sheet is to irreversible collapse, how soon we would have to cross that threshold to see very dramatic changes in sea level rise for centuries to come. So when you travel to Antarctica, you're incredibly privileged, of course. You jump out of this plane in the middle of nowhere, it's cold, it smashes you a little bit around the face as you exit the plane, and you get the sense how small you are, how wonderful this planet is. Very quickly afterwards, you do some training, you pack all your gear, and you end up in the field. So this was our camp at Roosevelt Island. We spent in total 3 years there to prepare and drill, and then Darcy Mandeno very kindly spent a 4th season cleaning up afterwards. But during those 3 seasons, we spent 11 months in the field. You get to know your fellow members very, very well. And I think it's one of these places where you add to your scientific skills also life skills that are very difficult to get in other places. You're not only the scientist, you are the mechanic, you are a flight air traffic controller, you're a medic, you're a chef, you're sometimes the counselor and sometimes the to be counseled. I think that spending the time in Antarctica with this amazing team gives you some skills that are applicable in many places in the world and helped me to deal with some of the management of larger projects, hopefully in a better way. But a lot of the work that we do as a scientist for the ice core work is really below the surface. So this is the drilling trench. Darcy Mandeno is operating the New Zealand Intermediate Ice Core Drill. This is one of 3 such drills available in the world. And they produce these beautiful sparkling ice cores. To us, they look like Tonga. To others, they might just look like frozen ice cubes. but they're rich of information, and they really revolutionize the way we think about the Earth system. While we were doing that work, there's also lots of other activities going on. For example, here's a couple of students that take a huge amount of snow samples at the same time. But every so often, the friendly Camboric team would come, when the weather would allow it, take our Tonga and bring it back to Scott Base, where it eventually would make its journey back to New Zealand, to the National Ice Core Facility at GNS Science. There, our international partners would come. For this particular project, they came for 3 years, every year for 3 months. And again, we operated in 24/7 operation with 12-hour shifts. And the people in this image here work at minus 20 or minus 30 degrees, depending on the work that we did, for 12 hours for 3 months. And I'm pretty sure that the national chocolate consumption in New Zealand went up during that time period. So here's when we cut the core, we prepare all the pieces, we do some initial measurements, and then eventually that ice is being put next door into a clean room facility where again we melt the core and attach that melter to a large number of instruments that measure in real time gigabytes of data that zoom back through time and tell us, as we melt the core, already some of its deepest secrets. At the same time, we're also taking thousands of samples, some of which are being analyzed in New Zealand and some of being analyzed with labs all over the world. So having gone through this massive effort, what did we learn from these baselines, from these invaluable opportunities to lengthen our observations? Well, this is a figure that Peter and I created a number of years ago, but I'm still very attached to it, and so I keep updating it. The top panel there shows you two worlds. The northern hemisphere during an ice age, covered with large ice sheets, and today's world, with just a small Greenland left. What is really interesting between the comparison of those two worlds is that the global temperature difference between those vastly different environments is just 6 degrees. So when we talk about future climate change of 1, 2, 3, or 4 degrees, these are remarkably large numbers. These are remarkably different climate systems and Earth systems that we're talking about. I don't think I need to explain too much about the actual graph that shows the beautiful Vostok ice core, the last 400,000 years of temperature. And then from the bubbles, we have released the samples to measure the actual content of the atmosphere of methane and CO2 concentrations. And of course, we can see how much in sync the temperature and the greenhouse gases is, which was one of the ways to demonstrate the close relationship of the warming that we see today from the greenhouse gases. And of course, in the right part of the image, we see that rapid increase in the greenhouse gas emissions. And so what did we learn from these comparisons? Well, we learned that methane has increased by 100% in the past 200 years. That is responsible for about 30% of the warming. And that it has a short lifetime, 6 to 12 years. So when we switch it off, methane will be gone fairly quickly. CO2 increased by about 50% in the last 200 years. Over the last 11 years, it increased every year by about 2 parts per million, which is the fastest increase in the last 65 years that we have a record from measurements, which means we're on the wrong track. We're still accelerating on our emissions. During COVID, for the first 6 months of 2020, we actually had a 4.6% decrease in CO2. We made up for it at the second part of the year. But to put into perspective of how big the challenge is that lies ahead, to achieve the Paris Agreement to limit warming to 1.5 to 2 degrees, we have to reduce greenhouse gases by 45% by 2030. So in the next 7 years, we have to find ways to halve more or less our emissions. And then, of course, come to net zero by 2050. In terms of temperature, when we look at these graphs, the temperature increase doesn't mirror the quick and dramatic increase in the greenhouse gases. And the reason for that is that 90 to 96% of the greenhouse gas warming is absorbed by the oceans, and about 2/3 of that by the Southern Ocean, which really highlights the importance of the Southern Ocean. Also, in June 2023, so just a month ago, global surface temperatures exceeded 1.5 degrees of pre-industrial levels. And the 4th of July was the hottest day globally on record. Of course, these records were broken as we just came out of a prolonged La Nina phase. We're now heading into El Nino phase. And during El Nino, the weather is usually somewhat warmer. So buckle up. These records are likely to be succeeded very soon. So while ice core records are really good to extend the observational record because of their tremendous resolution and continuous nature, when we want to look ahead, we actually exceed the time that is captured, or the variability that's captured in the ice cores, to look to the future. So here again, this is a figure from the IPCC that's a bit busy, but please let me talk you through. It's a very interesting graph that shows the beautiful Epica ice core record, 800,000 years of data. At the bottom, we have temperature, and at the top, you see CO2 concentrations. And then we go further back in time, millions of years and tens of millions of years, where geological sedimentary records have added to our knowledge of temperature and CO2 globally. When you now look towards the right, where we see the observations and then the choices of our emission pathways, you can see that with the CO2 concentration, the low emission future, so the Paris Agreement, is still higher in CO2 than at any time during the ice cores during the last 1 million years. We actually have to go back to the mid-Pliocene about 3 million years ago, where CO2 was 400 parts per million. And if we go to higher emission scenarios, such as the intermediate one, the yellow one, or the high emission scenario, the red one, we have to go back even further in time to the early Eocene. So what does that mean? Those three globes that are below that curve show you the temperature distribution during those times around the world. And we can see 2020, we already have a bit of warming in comparison to pre-industrial, so before global warming started. The mid-Pliocene, again, is quite a bit warmer than that. And the early Holocene just looks scary. It's unbelievably hot and very extreme in its temperature. So these reconstructions were incredibly important to now inform, verify, and interrogate models that try to predict the future. And if they can represent those paths well, our confidence in how they can predict the future increases. So on the right-hand side, you now see the predictions for some of our choices. So at the bottom, you see the Paris Agreement with a low emission scenario. And you can see 2100 is still a bit warmer than 2020. But 2300 actually is cooler again. So we're then starting, in this scenario, the Earth can recover. If we're going with the high emission scenario, the top panel, you can see that 2100 is warmer than the mid-Pliocene in many places. But 2300, the Earth is continuing to warm. And so by 2300, the Earth looks very similar. We're approaching conditions of the early Eocene, which are really very different, and I don't think any one of us understands what such a world would actually look like. So that's temperature and CO2. Now let's look what that means for sea level rise. Again, this is perhaps a graph that's a little bit old by now, from Andrea Dutton and colleagues in 2015, but it's so simple and so powerful that I'm still very attached to it. This graph compares CO2 concentration, global temperature at various times in the past, and seeks to understand its relationship with sea level rise. So we can see that in that current, in the modern present, we have 1 degree warming, and we're trying to figure out where we're heading with sea level rise. The last interglacial was a little bit warmer than today, about 1 degree warmer than today. CO2 was only at 280 parts per million, so way lower than it is today. But sea level was 6 to 9 meters higher already. If we go to what we call a super interglacial, so a slightly warmer interglacial yet again, 400,000 years ago, temperatures were 1 to 2 degrees warmer than pre-industrial. And sea level was about 6 to 13 meters higher. If we go to the mid-Pliocene, so 2 to 3 degrees warmer, then sea level was about 20 meters higher, a number that Andrew has tried to firm up. So of course now, in 2022, CO2 was 417 parts per million, which is about here, and so is currently certainly the future that we're heading for. So if we take all these baselines, the past reconstructions, what do they tell us about today? How different is today than from what the natural world should look like? This is again a summary from the International Panel on Climate Change, the IPCC, but nicely summarized by the World Resources Institute. And what's different is that CO2 concentrations are unmatched for the last 2 million years. Glacial retreat is faster than at any time in the last 2,000 years. The last decade was warmer than any period in the last 125,000 years. Sea level rises faster than any prior century for the last 3,000 years. The summer Arctic ice cover is smaller than at any time in the last millennium. Ocean warming is faster than at any time since the last ice age. And ocean acidification is at highest level of the last 26,000 years. So considering that our world is vastly different than what it should be, we can now turn to Antarctica and see how Antarctica is responding to that change. This is an image taken by Wong Sun Lee from the Korean Antarctic program at the Nansen Ice Shelf in 2014. When I started my PhD in the late 90s, I certainly did not expect to see in my lifetime liquid water running off an ice sheet or ice shelf in Antarctica, and definitely not in 2014. So Antarctica is changing in many, many places, and we could talk about a lot of different parameters, including the Ross Sea Marine Protected Area, the largest protected marine area in the world that is located in the Ross Sea region. But I would like to focus on just 3 parameters here: ice mass loss, sea ice changes, and Antarctic bottom water, because these are 3 parameters with their changes affecting every person on the planet. So we're starting off with ice mass loss. This is a beautiful animation by the GRACE satellite that measures elevation changes from 2002 to 2020. And what you can see in Antarctica here is these beautiful rivers of ice that are transcending to the ice shelves and exiting Antarctica through the ice shelves. So when I start this animation now, you can see the color change implicates the elevation change. Red and yellow means that it's lowering, blue is where it's growing, but the scale is just from +1 to -4 meters. And you can see that there's specific areas where the ice mass is losing very quickly, and we're now in a time where it has accelerated, where it's going faster and faster, in particular in West Antarctica, but also in some other areas like the Antarctic Peninsula and around East Antarctica. Here's a brief area where there's no data, and we're back to data, and we can say some very, very significant changes. If we now compare these changes with the underlying bedrock, so I'm just letting it run through again, but explain the bedrock in the meantime. Where you have the brown and yellow colors, you have large mountain ranges, many of them buried by the ice sheet above. And where you have the blue colors, the ice sheet itself is actually grounded below sea level, at times up to 2,000 meters below sea level. And you can see it's the blue areas, the areas where the ice sheet is below the sea level, where we see the largest change in the Antarctic. And the configuration of the ice sheet in these places means that it's susceptible to instabilities. And that's really worrisome, because it means once we have crossed a certain tipping point where the ice has retreated sufficiently, a self-reinforcing process kicks in where the ice sheet accelerates and accelerates in its loss until it's collapsed, even if we in the meantime switch off the forcing the greenhouse gas emissions. So this means that we can really commit future generations for centuries to come to sea level rise, even if maybe in 20 or 30 years' time we're successful in switching off our greenhouse gases. So in summary, what are the perils of sea level rise? Well, to date we had 20 centimeters of sea level rise. Since 2006, that sea level rise is dominated by the loss of glaciers and ice sheets. By 2050, about 800 million people will be affected by coastal flooding through rising seas and intensified storms at the coast. In a low-emission future, so Paris Agreement type future, we still will see a total of 50 centimeter sea level rise, which is absolutely locked into the system. So it's something that we need to mitigate and adapt to. In some places in New Zealand, that turns a 100-year flood into an annual event. In the last few months, we got a lot more acquainted to that sort of scenario. In a high emission scenario, a high emission future, more than 1 meter of sea level rise is plausible by the end of the century. And of course, we have these tipping points. If we pass these tipping points, and we believe that some parts of the Antarctic ice sheets are approaching this threshold of irreversible collapse, then future generations will pay the price no matter what our actions are beyond that triggering point. If you wanted to know a little bit more what sea level vulnerability is for a particular community you're interested in, your own property, or just generally around New Zealand, perhaps check out the New Zealand Sea Rise program. Richard and Tim leading this program, and this is an interactive map that is really a tremendous resource where you can zoom into almost property level to see future projections on sea level rise around New Zealand. So now I would like to move to sea ice. Not everyone thinks about sea ice a lot. For us, it keeps us awake at night, especially since over the last few years. Antarctic sea ice undergoes a dramatic transformation every year. During winter, it doubles the size of the continent, and it reaches about 20 million square meters in size, and then it shrinks to about 3 million square meters in summer. Antarctic sea ice is incredibly important. For the ecosystem, it's a habitat. It regulates the biological pump, so where organisms absorb CO2 and sequester it. It regulates nutrients, and is a habitat for some of the keystone species that maintain the food web. In a physical function, sea ice regulates how much the atmosphere and the oceans communicate. It limits biogenic gas production, and with that, the formation of clouds, which is hugely important and not well understood, how much it can protect or make an ice surface more vulnerable. It reflects incoming radiation and therefore limits solar-driven surface warming, something that we know really well from the Arctic. It stabilizes ice shelves, but with that it also stabilizes the ice sheets that sit behind these ice shelves. It's the formation of sea ice that develops dense water, and with that kicks off the global ocean circulation. It's the engine machine that drives our global ocean circulation, and with that, how heat is moved around the entire planet, and also how CO2 is being dragged into the depth of the ocean basins and sequestered, or at least taken out of the system for hundreds of years. So it's incredibly important. With the Arctic, we have come to see the decline in Antarctic sea ice. This is a graph that just shows the sea ice extent since 1978. In the Antarctic, we actually saw a slight increase that was mainly dominated by a sea ice increase in the Ross Sea. But something remarkable happened in 2016. In 2016, the Antarctic sea ice suddenly disappeared in a very significant way. In about 2021, we had hopes that it might recover. It was a little bit of a blip coming it back up. But then in 22, it continued to really crash to further minimas. To give you a sense of how big this change is, Antarctica lost in 3 years the equivalent that the Arctic lost in 30 years. So more or less in 3 years, the Antarctic caught up with all that sea ice loss that we have observed so sadly over the past 30 years. It's a massive change. And while we understand individual parts that caused some of that disappearance, we don't understand the trend. We're really puzzled by this very significant turnaround in Antarctic sea ice. This graph ends in 2022 because 2023 isn't finished yet. But here's a figure that captures from last week where Antarctic sea ice is for this year. So the colors show the time from 1979 to today, 2023, with the annual cycle of this remarkable transformation of sea ice, with the summer low of about 3 million square kilometers, heading into the winter where it reaches more like sort of 20. But you can see that the 2023 is well set for a new minima record, that yet again we see a stronger disappearance of the Antarctic sea ice. To understand what that means, we now need to look at the Southern Ocean. The ocean is not just a tub of water, but it's a very intricate system of currents that are driven by salt and energy differences. The engine for this conveyor belt that moves these currents around is the polar regions, where dense water is being produced and drives this entire conveyor. The important message from this slide here is that if you change one aspect of the ocean, you cannot expect that it doesn't communicate through the entire ocean basin, because it's so connected. And it's more connected in the Southern Ocean than anywhere else, because it is connected with all the major basins around the world. So now we look in more detail of how this works, the engine room. So we're back in the Ross Sea, under the ice shelf, where sea ice is forming in the front. And as sea ice forms, it rejects really salty brines. If you use sea ice to cook spaghetti, for example, they're quite edible. If you were to try to do the same with marine water, it would be quite salty. So this means that under the sea ice, the water is even saltier than it normally is. And because it's very cold and it's very salty, it's heavy, and so it just sinks. And there's a lot of it, and it cascades and waterfalls down the continental shelf, and it's the engine that moves the currents around the entire globe. So changes in sea ice, changes in the ice shelf, changes in the ocean vastly have implications for the entire global ocean circulation. So how has it changed? Antarctic bottom water, as we call that, accounts for 40% of the ocean, global ocean volume. So it's an enormous dial to turn. In the Weddell region, so the other side of Antarctica, we've already observed a 30% reduction in the formation of Antarctic bottom water, which is linked to sea ice changes since 1992. It's really important to understand that this is the lower limb of that global ocean engine, and if we change that, that engine will change. And with it, the uptake of CO2, which could result in more CO2 remaining in the atmosphere, and also the distribution of heat and where it goes into the world. Overall, the Southern Ocean has experienced warming because it's absorbed the warming from the greenhouse gases. That's in the deeper ocean. The surface ocean has cooled, and it is cooled because of all the melt of the ice sheets, pouring this really cold ice water from the ice sheets into the ocean, which actually led to a very significant cooling of the surface waters where that occurs. It also has freshened, and again, the same reason, because of the melt of the ice sheet, the flux of fresh water into the ocean has reduced its salinity. We see an increase in acidification, and that is because of the uptake of CO2, but also because the ocean has gotten warmer, and with that has less capacity to uptake CO2. And we see a reduction in oxygen because of the change in the ocean circulation. So if I would have given that talk about 5 years ago, I would now have gone into, so what does that mean? Where are these changes leading us into the future? But I think over the last few years, we have all come to terms with it, that we're no longer just predicting the future, but actually the time of the age of sort of consequences has arrived. We are seeing them now. These are now images from New Zealand. This is Lake Ohau, a very devastating forest fire. But of course, we have also been very familiar with the many tragedies around Gabrielle, the human aspect of this trauma, but also more broadly the impact on our economy with droughts and floods, the impact on our infrastructure with rising seas, and the change in our environment through slopes and changes to the vegetation and climate parameters through extreme weather events. One very abstract way of looking at this is through numbers. And this is a figure from the Swiss Re Institute, the reinsurance, that monitored globally insured losses since 1970 in US dollars, billions of dollars, inflation adjusted to 21 values. And you can see in this graph, blue is for earthquakes and tsunami, green is weather-related, and man-made disasters. And you can see that the green bars not only dominate this increase in insurance, but that it's a very quick increase in the last few decades. Of course, these are the insured losses. And so here is a graph by its sister company, the Munich Reinsurance, which shows total losses and insured losses of weather-related events. So the yellow or orange graph here is very similar again to the green bars in the previous figure. And you can see that the total losses that now include the uninsured ones are rising much faster than the insured ones. We can look at this for New Zealand. So these are data from the Insurance Council of New Zealand since 2012. And you also can see that extreme weather claims have increased over this time period. Of course, we don't have 2023 on this graph yet, but we know from those data that about 675,000 people, so 1 in 7 across New Zealand, live now in an area prone to flooding. 72,000 people live in areas projected to be subjected to extreme sea level rise. 5% of New Zealand properties would face an insurance premium for their flood risk of 1% of their property value if it was properly assessed for their property, which would mean $10,000 per year for a $1 million home. 2% of houses would face a 2% premium, so $20,000 for a $1 million home per year for flood protection. This certainly explains also the increase in uninsured losses, as well, of course, as the global footprint of where these damages are most prevalent. Cyclone Gabrielle is thought to be the costliest Southern Hemisphere tropical cyclone on record. In April, Treasury estimated that including the preceding floods in Auckland, they are difficult to keep apart, lies between 9 and 14.5 billion. And just last month, the Insurance Council of New Zealand estimated that the claims that they've received by June, which is over 100,000 claims, would accumulate about $3 billion of insured claims, which of course also leaves somewhere in the order between 6 or 11 billion uninsured losses in New Zealand. So we are at a watershed moment. We have to decide what our future should look like. We cannot afford climate change. Can we afford not to do something? This figure of the IPCC resonated in particular with my thinking about the future and how we might demonstrate or think about it on a personal level. It shows the temperature history from 1900 till 2020, and then it gives us choices for the future. But it ties it back to a person and when this person is born. So here you can see a person born in 1950 is currently 70-year-old and is already dealing with some significant climate change impacts. However, the person who is born now or is a child right now, our choices in the next even just 7 years will determine the future of the life and the livelihood of this person. So the very low and the low scenarios are the Paris agreements, and you can see that by the end of it, the warming actually could stop and we could see a reduction in temperatures again. For the intermediate and higher emission scenarios, the warming will not stop at 2100, but will continue to rise. This figure also demonstrates that even if we miss the Paris Agreement, that we cannot stop. It is not just one threshold and everything is lost. It is a very important threshold, and we should collectively work to achieve it with everything that we can. But if we cannot achieve it, the intermediate scenario is still better for that person than the high or the very high. So every reduction that we achieve is worth it. And if we can achieve enough to stay below the Paris Agreement, then overall we win as humanity. So I thought I'll finish on this particular slide and bring you back to Roosevelt Island. This was in a morning, I think 4 o'clock in the morning, I went to read out the weather for an incoming aircraft, and I saw this rainbow. You can see bows in Antarctica, but normally they're white. And they're white because the atmosphere is frozen. So this picture has tremendous beauty and irony and sadness all in one, because the colors in this rainbow showed us that there's liquid water droplets in the atmosphere. And what an irony. Here we are drilling to find out how close the West Antarctic ice sheet is to irreversible collapse, while for the first time we see liquid water at almost 80 degrees south in a cold part of Antarctica that tells us that perhaps we're a bit too late and the future is coming faster than we think. So the window of opportunity to secure a livable and sustainable future for us all is rapidly closing, the IPCC warns us. To achieve the Paris Agreement, we need to reduce greenhouse gas emissions by 45% by 2030, and we need to reach net zero by 2050. It is incredibly important that we try everything we can to come to this goal, but it's equally important that if we miss the goalpost, that we do not give up. One thing that we cannot afford is inaction. The future that comes with it is not acceptable and not affordable to any of us. Ngā mihi nui.
Tēnā koutou, tēnā tātou katoa. I'm Rob Mackay. I'm the director at the Tipuna Pātiotia Antarctic Research Centre, and it's my honour and privilege to propose a vote of thanks for Professor Nancy Bertler's inaugural lecture. Greetings also to Nancy's family, her mother Sissy and her partner Dean, who many of us in this room, as Nancy pointed out, also know through the Antarctic community. It's our pleasure to have you joining us here today. So in this inaugural lecture, we've been honoured to hear Professor Bertler provide an insight into Antarctica's ice sheets, the critical insights they reveal to our future, and why our response is a matter of urgency. We are living in the age of consequences. From someone that knows Nancy very well, and I actually have known Nancy since she was doing her PhD, I was a master's student here at the time, what I think needs to be emphasised in here is just not only the fact that she can cover this broad range of communication about the impacts of Antarctic climate change on the global systems, but also her fundamental leaderships and achievements within her specialised discipline of ice coring, and we saw just how impressive that was with the Roosevelt Island work. Now, a few years ago, I followed in Nancy's footsteps. I applied for a fellowship that she went for, the Rutherford Discovery Fellowships, and one of the key aspects of that to get one of those awards is leadership. And so I thought, as you do when you're doing an application, you look at a previous example, and I took Nancy's leadership page. And I have to say, I was pretty intimidated. I pretty much put it away straight away because there was no way in hell I was going to be able to emulate those achievements. They were very, very unique. I couldn't even come close to it. So it was very clear, Nancy pointed out at the start of her talk that she was standing on the shoulders of giants. And, I think nowadays, and particularly at that time, even looking at that leadership document, it was very clear that people were starting to stand on her shoulders at that point. And now the entire Antarctic community in New Zealand is standing on her shoulders as her leadership within the Antarctic Science Platform. So as a PhD student, she came over here, as she pointed out in the introduction, as Margaret did, that we didn't do ice coring in New Zealand. She took it on as a PhD student. She created this whole capability out of her own hard work and vision. By 2004, she had just finished a PhD. She built an ice core facility out at GNS Science. I mean, who does that 1 or 2 years out from a PhD? It's incredibly impressive. She's since become a world-leading expert in ice coring. She is recognised on the international stage for this work, leading major panels with the Scientific Committee on Antarctic Research, and culminating in the Roosevelt Island Climate Evolution Project. She had 13 field seasons under her belt and then leads a $12 million project in Antarctica with 9 different countries. And it was a remarkable success. She coordinates science at national and international level. As I said, she's director of that Antarctic Science Platform. That's a $49 million program for the entire country, working to solve some of the biggest challenges globally and placing New Zealand as leaders in understanding Antarctic climate change impacts. So what we've seen tonight is Nancy's passion and leadership in climate change science and communication more broadly. This is something she's always been at the forefront of. Even as she was coming out of that PhD, she had the vision to set up the first dedicated climate change course in the university. This provides a comprehensive view, not just of the science of climate change, and as you saw at the end of Nancy's talk, some of the impacts on the economy, society, as well as sort of guiding how government strategies might mitigate and adapt to the threat of climate change, which was emerging at the time, and now we're living, as Nancy says, in the age of consequences. So she used her vision, her knowledge, and her connections to experts. It's the ability for her to find connections across communities that is just so remarkable. And that was something she developed in that course very early on, bringing in experts from downtown, from government, to talk to our students and train the next generation of scientists, policy makers, to understand how to manage this threat. So it's my privilege to offer this vote of thanks to Nancy. She's provided an example of leadership and scholarship that, in my view, is the very definition of what a professor should be. And I welcome you now all to join us in the Hunter Common Room for refreshments and some. But first of all, just ask you to have a round of applause for what was really a fantastic lecture. Thank you.